Hello, chemistry students. We are moving right along and we are moving into an abbreviated version of understanding phase changes, a little bit about gases, but not too much. So essentially we're going to talk about this picture right here where we're looking at a phase change, and we've spoken about this before. Phase changes are just simply a change of state. We've used the terms, let's just stick with water, the solid form of water, which we like to call ice, right? And we can transform that into liquid water if we add energy. And we can translate that into, or transfer that into, change that into gaseous water. We call that steam, obviously, sometimes. And we just want to have a visual in our heads of what those actually look like in terms of their organization, in terms of the structure, the proximity of the particles, and the energy involved in those particles. And so you might guess that this is our lowest energy. We've spoken about energy in chemical reactions, and so we're honoring that sort of idea with physical changes. And this is the highest energy. We probably know that we call this phase change right here melting, right? So we take ice out of the freezer and we melt it. So when we talk any solid and we go through melting, which is different than chemically reacting that particle, right? And then when we do this, we call this boiling or evaporation. When we go the other direction, right, we can go this direction, we can call this condensation. And when we go this direction, we call this freezing. And again, those apply to everything. So not just liquid, not just water, that substance that we're super familiar with, but also other substances, we can use that same terminology. We can actually skip the liquid phase and go right to gas phase. Some of you that are skiers may have seen this before. If you've ever played with dry ice before, you know that this phase change is called sublimation. And when we go the opposite direction, the opposite of that, skipping the liquid phase, maybe you've heard the weather folks talk about freezing fog. That's called deposition. So it basically is an energetic phase where it just skips that altogether. What we want to make sure that you get is that there's energy involved, okay? And how is this different than a chemical change? Well, we know that we've written this down, that when we decompose water, we could break it down into its elements, right? So we break bonds when we do that, right? This is a decomposition. We know there's energy involved. Basically, we have to add energy to this. This is an endothermic reaction. You can do this with electrodes. You'll do this in your biology 160 class probably. We want to balance that equation so that we have the right number of atoms on each side of the equation. So we have equal particles here and here and here because they're just breaking bonds and rearranging, right? So we also have these phase changes, right? So when we go from solid to liquid, okay, this is also an endothermic reaction. We have to apply energy to it, but that energy is a little bit different. That energy is in the process of taking this organized structure, these particles that are really close together and organized maybe into a crystal, and breaking them apart, wiggling them around. These particles are moving a little bit faster and they have that energy stored in them. They're more chaotic. They're not as organized as the solid form. And then you can think about the fact that when we go from liquid water back to gas, right, that also takes energy. And that energy is stored in the gas. And then when you go the other direction, so if we were to reverse this reaction and go this way, energy would be released. And if you've ever had a steam burn, you probably know that energy is released also when we freeze water. So we have to take that energy out of it. So basically, again, there's energy involved in a phase change. We just want you to make sure you understand that part. We also want you to make sure you understand the difference between a phase change and a chemical change. Okay, as we go there, we're going to start talking about that energy in a different way. We're actually going to draw an energy diagram like we did before. So before, what we did was we talked about endothermic and exothermic reactions, just a quick review. And in one case, we started low, right, with our reactants. and we went up over an activation energy barrier to our products. And we called this an endothermic reaction, right? And that kind of is a way to think about this too, except for this applies to chemical reactions. This is your heat axis, and this is your reaction coordinate, we called it. And then we said exothermic reactions. Let's get a different color here. We said exothermic reactions look like this, right? We have our reactants up here. We go over that energy barrier, and we can end up down here with our products. This is exo, right? And again, this is our reaction coordinate, and this is our heat. So we can think of that, again, when we look at these diagrams, we're speaking specifically about energy diagrams for a chemical reaction, for a chemical reaction. So I want to contrast that with what it looks like when we're talking about a physical change. So let's go through a phase change diagram from -15 to 110 degrees Celsius, and we want to sort of label all the parts. So it looks a little bit different. So we're going to have our vertical axis and our horizontal axis. This axis this time is going to be temperature. And this axis right here is going to be energy. Okay, and we're going to start at -15. So we're going to put that in there, degrees Celsius. And we're going to go up to 110 degrees Celsius. And we're going to look at how that might contrast. So you can imagine, if you will, just basically taking some ice out of the freezer, and it's at -15 degrees. And you're basically going to put that ice in a beaker. So you put a bunch of ice on a beaker. You put it on a hot plate. Okay, so you've seen one of those now, and you turn it on, and you plug it in, and you just add energy, right? So we're adding energy to this. So that's kind of what's happening. And so we just add energy, right? And so we know that that ice is going to melt. And so we want to think about what that might look like. So basically the idea here is as I add energy, the ice has to warm up, okay, to the freezing point. And we know, most of you guys know that the freezing point of water is 0 degrees Celsius. And then something super interesting happens. This levels out, even though we're still adding energy, it levels out until we get all the ice to melt. And so basically at this point of the graph, right, there's a mountain of energy. We call this the heat of fusion. We're going to use that in lab. And the heat of fusion for water is 80 calories, and these are heat calories per gram. So for every gram of ice that you melt, it requires 80 calories. And that process is this change between this organized crystal structure and this sort of more random moving more particles of liquid, right? So that energy is there. So then we continue to heat it, and we get up here, and we just see this rise in the temperature from 0 to, maybe you know that the boiling point of water is 100. And again, something super interesting happens. Basically, this is going to level out, but it's going to level out for even longer. As we change the phase between liquid and gas, and then we continue to heat it, and we can heat up the gas until we get wherever. You can go actually to a third stage of matter, which is called plasma, or a fourth stage of matter, which is called plasma. Okay, so let's talk a little bit more in our next video about those numbers. I'm going to just get this down here, right here. We're going to call this part right here. This part right here is called the heat of vaporization. And it's for water, it's specific, it's bigger, it's 540 calories per gram. So in our next video, we'll continue that conversation. Thank you so much for listening. Hope you're having a great day.